Dear students, the last class we discussed some uh, applications of Lagrange's theorems, and in the finally we have to prove that uh, the converse of Lagrange's theorem is not true in general. Today's lectures we discuss the Fermat and Euler theorem. Last class, one of the applications of the Lagrange's theorem, we proved that if a group G is of a order of a group is a prime, then every non-identity element generates the group of G. So this means this is the nice application of that result to number theory, include a group theory approach to famous theorem of Euler on congruence and its corollary, the little theorem of Fermat. The theorem is this. We have to start today's lecture with this. Let G be a group generated by G be a cyclic group of order n, and M be a positive divisor of n. Then the number of elements of order m in G is phi m. So we can say that simply is m is a positive divisor of n. Then the number of elements of order m in G is phi m. So let us prove this. Suppose H is an element of order m in G, then the subgroup generated by H must be a unique cyclic subgroup of order m. This implies that all elements in G with the order m belongs to this cyclic subgroup. This means clearly we can say that if we have to choose a subgroup generated by H is a unique cyclic subgroup of order m, this means all elements in G of order m belong to this cyclic subgroup. So means if we have all the group elements of order m belongs to the G is the member of this subgroup generated by H, because this is a unique cyclic subgroup of order m. So therefore we consider G as a cyclic group of order m. So now we can consider G as a cyclic group of order m. So our task is now to determine which elements of this group have order m. So we have to find the elements of this group have a order m. According to this, the theorem is saying that let G be a group and G is the element with the finite order, then order of G to the power k is equal to identity if and only if n divides k. So the element of G to the power k has order m if and only if we can say that the GCD of km is equal to 1. So GCD, this means identity can divides k, then GCD of km is equal to 1. So by the definition, the number of such integers k with k lies between 1 to m is phi m. As stated in this, the elements of a group precisely of the form G to the power I lies between 1 to m, but since G to the power 0 is equal to m is equal to identity, we can equivalently consider G to the power I with this theorem. So now we can say that clearly we have to complete this theorem result. This means the number of such integers k is phi of m is there. So clearly this is very trivial. We can say that if we have a G is a finite cyclic group of order n and m be the positive divisor of n, then the number of elements of order m in G is phi m. So now we have to just, for example, I take this, how many generators does a cyclic group G of order 504 have? So we have to, by the theorem, we say that if we have a group G is a cyclic group of order m, then m is the divisor of this G, then there is a phi of m is there. So we have to write this theorem. G has a phi to the power phi of 504 generators. Now since 504 can be written in the form of 2 to the power 3, 3 to the power 2 into 7. So we obtain the properties of Euler function phi. Then we have to phi of this 2 to the power 3, phi of 3 to the power 2, and phi of 7. Phi of 7 is equal to, we have a clearly is equal to 6. So we have to write in this form phi of 504 can be written in the form of a phi of 2 to the power 3, 2 to the 3 square and 7. Now by the property of a Euler function, we can easily write in the form of a phi of 2 to the power 3 and phi of 3 to the power 2 and phi of 7. Now we have now that we have a result is phi of p to the power n, then you have to write as a p, is this p to the power n minus p to the power n minus 1, and then clearly we have to write a phi of a p is equal to, you have a write in this form. So clearly we have to any prime p, then it can be written in the form of a n p to the power n and p minus p to the power n minus 1 form. So this is the 2 is a prime, so 2 to the power 3 can be written as 2 to the power 3 minus 2 to the power 3 minus 1 is equal to 2, and similarly 3 is also is a prime, so phi of 3 to the power square 3 square minus 3 to the power 1, and 7 is also prime, 7 to the power 1 minus 7 to the power 0, and then you have 7 to the power 1 is equal to 7, 7 to the power 1 is equal to 0 is equal to 1, then clearly is equal to 6. So we also know that if you have a phi of p, we simply say that p minus 1, the total value of this Euler function phi of p is always equal to p of minus 1. So we can simply write this is the 2 to the power 3, 8 minus 4 is equal to 4, then we have a 9 minus 3 is equal to 6, and the 6 that is equal to 144, then hence G has a 144 generators of this group. So clearly if we have a group has a order is a 554, then this m divisor, then we have a just has a phi of m generators, and then phi of m generators means we can simply say that this is equal to, we have a 144 generators of this group. Now the following theorem is an important result in the number theory. Now we have to move to the next theorem. The theorem is in very important result in number theory due to Leonard Euler, and then we can say that is a say that if r and n are be integers such that n greater than 0 and the GCD of Rn is equal to 1, then r to the power phi n congruent to mod of n. So Euler's theorems clearly say that if we have a r and Rn into integer and GCD of these two are equal to 1, then r to the power phi n congruent to 1 mod of n. Now we try to prove this theorem. Let G can be written as a equivalence class by the, you know that by A congruent to B mod of n, we can write a equivalence class is this is A congruent to B mod of H, like this, the AB inverse is. So this is right in the equivalence class. So let G can be written as a equivalence classes of a R is an integer less than n and relatively prime to n. Be the set of a residue classes under the multiplication. So we just take a G as a this in the form of a equivalence classes, residue classes under of this multiplication. Now we just say that the G form a group and the order of a G is phi n. So by corollary, if G is a finite group of a G, then G to the power order of a G is equal to identity, one of the applications of Lagrange's theorem. So then we can say that G, if we have a order of a G form a group and order of a G is phi n, then by this result we can say that if this r to the power order of a G is equal to we have to can say that order of a G is equal to, we have phi n, and this by result order of a G to the power n is equal to identity, so this is equal to 1. So r to the power G is equal to, we have to say is equal to identity. So r to the power order of a G is equal to identity. Now if r to the power G is equal to identity means is equivalence class of a 1, then this r to the power order of a G can be written as a, because order of a G is equal to, you have a phi of n, then we can write equivalence classes of r up to phi n times, and then this is equal to identity. So this means equivalence class of a r because r equivalence class of r to the power G is equal to equivalence class of an identity, then we can say that this R to the power order of a G, because order of a G is equal to has a phi n elements. This means equivalence classes of a R can be written into the phi n times. So if it written as a phi n times, we can just say that this also by the property of equivalence classes we can write in the R, and this is equal to, again there is a phi n is equal to identity element. So this can be written as a R in the equivalence class of a product phi n times of a R. So we just write into this is equal to identity. So but this means this can be written as a R to the power phi n and then is equal to identity, and this is identity means equivalence class of identity. Then we can say that equivalence class of this is the same as this. This means we can say that R to the power phi n congruent to mod of 1 mod of n. So by this we can use the definition of this A congruent class of A is the same as a congruent of a B, implies A congruent to B mod of n. If we have a mod of n is there. So we can say that simply we can prove this result is very trivially. We can say that R to the power phi n is the same as the congruent to 1 mod of n. We have to trivially we have to prove in this case. So we prove this R to the power phi n is equal to congruent. This result is completely proved. Now if we consider the special case of Euler's theorem where n is equal to p is a prime number, and recall that you know that phi to the power p phi of p is equal to p minus 1, we obtain the following result known as a Euler-Little theorem, which discovered by Pierre de Fermat. This theorem states that a to the power p minus 1 congruent to 1 mod of a p. This is trivially we have to using the previous theorem. In place of a n we have to writing the p, and using the definition of a phi p is equal to p minus 1 for any integer a such that a is not divisible by p. This theorem is a special case of Euler theorem and provides a fundamental result in number theory concerning prime numbers and modular arithmetic. So now we have to state the Fermat's little theorem. If p is a prime and a is any integer not divisible by p, then a to the power p congruent to a mod p. Now so we have to just try to prove this result. Because we have to proving this, so we have to just say that a to the power p minus a, we have to prove that in the form of this a to the power p minus a congruent to 1 mod of p, and then we getting, if this is happening, then we have to get the this result is true in this case. So let a to the power a minus p, a to the power p minus a, then this can be written as a to the power p minus 1, and we can write a to the power p can be written as a to the power p minus 1, and then if we take a is outside, so this a to the power p minus 1 minus a. There are the two possible cases are there. One is if p divides a, then if p divides a means if p divides a, then p must divides this whole of this thing, and then this implies that p should divide a to the power p minus a. If p divides a to the power p minus a means, if you know that if a divides b, then you can say that a congruent to b mod of n whatever this under this condition. So we can say simply is this, then if n divides a, we can say n divides a minus b, so we can say a congruent to b mod of n. By this definition, if p if p divides a, then p if divides a, this p should divide whole of a, and this p divides whole of this thing, then p should divide a to the power p minus a. If a divides this thing, then we can say that if p divides this a to the power p minus a, so p divides a, this p should divides a, and p should divides whole of this, and p divides into this form, and p divides this form, we can say that p if divides this means a to the power p congruent to a mod of a p, which complete the in the case if p is divides a, the result is true in this case. Now next we have to try to for the second case, in case we have a p does not divides a, then if p does not divide a, p is a prime, then a and p are p a is relatively a prime to a, and if a is relatively prime to p, hence the Euler theorem is saying that a to the power 5p is equal to congruent to 1 mod of p. So if p does not divides a means p is a prime number, then a and p are relatively prime, and if a and p are relatively prime, then by using the Euler's theorem, you are saying that if p is a prime and a is any integer, then a to the power 5p congruent to 1 mod of p. And then by this Euler theorem, we can say that now since phi of p is equal to, we have a p minus 1, this implies that we can a to the power p minus 1 congruent to 1 mod of p, and this means this can be written as a p if this thing is equal to happening, then p should divide a to the power p minus 1 minus 1, then by the definition of this modulo condition, so p should divide a to the power p minus 1 minus 1, and then if p divides this thing, we can say that this can be p should also divides a into is quantity in this form. If p should divide this, then p must divide of this form also, and hence if p divides this is nothing but is equal to a to the power p minus 1 minus 1 is the same as a to the power p minus a. So that means p should divide a to the power p minus a, and if p should divide a to the power p minus a, then means we can say that a to the power p is congruent to a mod of p. So we just say in the both the cases, if either p divides a, then we have to show that a to the power p congruent to a mod of p. If a to the if p does not divide a, then we use the Euler theorem, and then by the Euler theorem we can say that if p does not divide a means p and a are relatively prime, and p and relatively prime, then a to the power phi of p is equal to congruent to 1 mod of p by the Euler theorem. Then by using the property of a phi p, we have to prove that a to the power p is equal to congruent to a mod of a p. So in both the cases we have to, and showing that if p divides a and p does not divide a to the power p congruent to a mod of a p. So we can say simply this complete the proof of this theorem. So we simply prove this theorem. Now we have a one problem, and that problem is saying that find out the right cosets of H and K in G, where G is generated by G is a cyclic group of order 10, and H is generated by G square, and K is generated by G to the power 5. So we have to find all the right cosets of H and K in G, where G is generated by G is a cyclic group of order 10, then is order 10 means G to the power 10 is equal to identity, and H is generated by G square, and K is generated by G to the power 5. So G is order 10, then G generated by G. So the elements of G are G, G square, G to the power 3, and so on. G to the power 10 is equal to, you have a identity. So we have a identity to all these are the generators of this. So G is a cyclic group, then generated by G, then G is of the form of this. G can be written in the form of identity up to G to the power 9. Now H is a generated by this and the group of order 10. So G to the power 5 is equal to identity. G square to the power 5 is equal to identity. So we have a G square 4, 6, 8, 10 is equal to identity. So this is the elements of this are G square, G to the power 4, and G to the power 5 square is equal to identity. So you have a G to the power 5 and identity, only there are two elements in this case. So order of a K you have is equal to 2, and order of a h you have a 5 and order of g is equal to you have a 10. So we can clearly giving this form. Now you see clearly, if you see this h is a subset of a g, and h is a subset of a g, is as clearly identity element is there. If you take a g square g to the power 4 is equal to g to the power 6, also the element of h. And now if you take a inverse of elements, you can also getting the identity element. You have to identity element is here. Now you can take any two elements, we take this giving the identity element. So you have a g and g to the power 2 into g to the power 8 is equal to g to the power 10 is equal to identity. Then these two are inverse of each other. G to the power 4 into g to the power 6 is equal to g to the power 10 is equal to identity. Then these g to the power 4 and g to the power 6 also the identity. Here is the identity element and g5s are there. Is clearly we can say that h is a subgroup of a g and k is also subgroup of a g. So this is clearly we have to write these h and k are the subgroup of a g. Now we have to try to find the what is the right cosets of a this h and k in g. So hg is equal to, you just say that hg, so you have a h is equal to, you have a I just write in the form of h square g square g ki power 4 g ki power 6 and g ki power 8 into identity. This is g. Now we have a right coset h of g. You have g to the power 3, g to the power 5, g to the power 7, g to the power 9, and you have a g. Now if you take a g of square, so you have a g square, then you have to write a g ki power 4, g to the power 6, 8 and 10 is equal to identity and g square. And then you see this is the same as a we have to getting the h is there. If we have to take a g to the power h3, if you take a g to the power h3, then you have a g to the power 5, g to the power 7, g to the power is 9 and g 3 is there. So g to the power 3, g to the power 5, 7, 9 and g. So this is nothing but is equal to hg. If you take another g to h, g to the power 4, if you take a 4, then you have a g to the power 6 and g to the power 8 and g to the power 10 is equal to identity. You have a, and then g square and g to the power 4, and again you have to getting this is equal to same as this is equal to h. So whenever we have to giving the power of a even, we have to getting the h. When we have h5, if we take h g to the power 5, and this form you have a, if take a, this g to the power 7 and g to the power 9, you have a g to the power 3 and g to the power you have a 5. So g to the power 3, 5, 7, 9 g, then again you have a hg. So there is means we have only two types of a right subgroups is we getting, either h and hg types. So this means similarly we have to just h4, h6 even we have to getting h. Whenever g to the power odds we have to getting the hg. So there are only two distinct right cosets of h in g with h and hg. It be noticed that you can just say that if we have a h intersection g is equal to, you have a phi, and g can be written as a h union hg. So h union hg is generated by this partition added into g, and then we can intersection is clearly is a both are the non-empty. You can just say that you have a h is equal to simply is equal to this form, and then there is a intersection is clearly is a empty set. So we have to find this, there exists for h has only two distinct size coset. Now similarly we can find for the k. Now you have a k is equal to, you have a g to the power 5 into identity, then you have a k of g is equal to, you have a g to the power 6 into g, k of g square is equal to, you have a g to the power 7 into g square, g k to the power g k g to the power 3, g to the power 8, g to the power 3, then you have a similar fashion k to the power 4 k to the power 5 is equal to, you have to getting is equal to k, then k to the power 6 again you have to get in the kg, then k to the power 7 you have to get kg square, and then similarly we can, if we get to the kg to the power 8, if you kg to the power 8 is equal to, you have a 3 and 8, you have to get a 3 and 8 you have to kg square, and the kg of 9 is equal to kg power 4, and k of e is equal to, you have to getting of identity. So we have to calculating all the elements of a because g is, you have a identity, and g to the power 9, and we have to calculate all these things. So we have a 1 right coset, then we have a 2 right coset, g to the power 3, 4, and then we have to this k to the kg to the power 5 again k. So we have a 1, 2, 3, 4 are the, and 1 is a k itself. So this means we have a there are 5 right cosets, k, kg, k square, and this. So we have a total number of 5 right cosets of g. In G, these right cosets of K are disjoint, and that is they have a no element is a common, and then also you can see, and then if take a union of this is equal to this form K union kg union kg square union of a k g sorry k kg square union of a k g to the power 3 and k of g to the power 4. So this means we can simply say that this g is the clearly we write into the this form. Now I just say that another problem we have to just say that let G be a group of order 30, how many cosets of g to the power 4 are there, and list them. So we have to try to find the how many cosets of g to the power 4 are there, and we have to try to list them. Now g to the power 30, you can order of a g is equal to element is 30, then g generate a cyclic group of order 30. So determine the number of cosets of g to the power 4 in this. We need to compute the index of this which is the number of distinct coset of g to the power 4 in generated by this g. So first we find the order of a generator. Then you know that the order of a generator is nothing but is equal to order of a g is 30 and GCD of a this, and since GCD of a 30 and 4 is equal to 2, so this means order of a this index of a this is equal to 30 by 2 is equal to 15. So we can simply say that there are 15 distinct cosets are there. So there are 15 distinct cosets are there of g to the power 4. So 2 cosets of g to the power the list 2 list the coset, the 2 coset of g to the power are in g are g to the power 4 and g into generated by g to the power 4. Now expanding these coset explicitly we get this form g to the power 4 is the form of this thing, and then because no all these elements are here, now g into g to the power 4 is into this form, and now you see these two are disjoint, and clearly you have a just say g to the power 4 intersection g of g to the power 4 is equal to empty set, and if you take a union of these two, then you clearly this is equal to you getting the g, and g is nothing but is equal to generated by g to the power 4 union g of generated by g to the power 4. So we can simply say that there are only 2 cosets are there, distinct cosets are there, g to the power 4 and g into this by the index, because we can say simply is this. Now we have to compute the index of this into g to the power 4. So g to the power 4 and g giving the index is equal to 2. So there are 2 distinct coset of g to the power 4 in g, and this means we have to say simply this can easily we have to find of this. There are only the 2 distinct cosets of g to the power 4 and g. So these are the complete the solution of this problem. And now I just close this section with this problem. I just say write for each group G and subgroup H, find all the left cosets and right cosets of H in G, where G is equal to Z and H is equal to 3Z, and then there are the few of them. I'm not going to try to solve all of them. I will just try to few of them in this. I just interested is A. We try first one is A, and then let's see. Okay. So A is equal to Z and H is equal to 3Z. So under addition, this is a group. Then we can say that simply H plus 0 is equal to 3Z, H plus 1 is equal to, in this form, H plus 2 is equal to 2 plus 3 form, and then we have to just say that the right cosets are the same as the left coset because Z is a abelian. So there are only 3 cosets 3Z, and then you have a 1 plus 3Z, 3Z, and then we have a case 2 plus 3Z. If you take a H plus 3, then you can say that same as a 3 plus you have a 3Z is equal to the 3 plus 3k, and then this is nothing but is equal to 3 times of a 1 plus k, and this is the same as you can just say that 1 plus 3Z, and then same as a H plus 1. So this means this is a H plus 3, so H plus 1 and H plus 2, then we have a 3Z, and this 1 plus 3Z and 2 plus 3Z are the 3 distinct left cosets or right cosets are the same because here we have a group is an abelian form. We have to third one, we have to just G is equal to Z12 and H is equal to 3Z12. So this means you have to note that the Z12 element 0 to 11, and then we have a 3Z12 is the element of under the 12 addition modulo 12. So this is 3 times, you have a 0, 3, 6 and so on. We have to write into this form. So Z12 is equal to 0, 1 to 11, and then 3Z is equal to, we have only 0, 3, 6 and 9. These are the elements. So now we have to calculate the 0 plus H is equal to, you have a 0, 3, 6, 9, and that is equal to H. Now if you take a 1 plus H is equal to, you have a 1, 4, 7, and then you have a 10, and then you have a 2 plus H is equal to, you have a 2, 3 to 5, 6 to 8, 9 to, you have a 11. Now you have a 3 plus H is equal to, you have a 3, 6, 9, and 9, 3 is equal to, you have a 9, 3 is equal to, you have a 12, and 12 is equal to 0, and this is equal to, you have a same as a H. Now we have a 4 plus H can be written as a, you have a 4, so you have a 7, you have a 10, and 9, 4 is equal to, you have a 13 is equal to 1, this is equal to 1 plus H. Then you have a 5 plus H is equal to 5, 8 is a 11, you have a now 9 plus 5 is equal to 14, you have a 2, and that is the same as you have a 2 plus H. So in general we can say that only we have a H, then 1 plus H, and then you have a 2 plus, there are the 3 distinct cosets are there. So H plus 0, H plus 1 and H plus 2 are the left cosets are there, and then again this group is an abelian group. So we can say that the right and left cosets are the same in this case also. Now I try to one more. I just group is generated by this H8. So we have to write the element of a Z24 is this form, and H is generated by 8. So 0, 8 and 16 are the element. Then in this case again we have there is a 3 distinct cosets are there left, and the right cosets are the same as the left because again Z24 is an abelian group. Now I just this one let G be generated by this, and order of this G is equal to 20, and H is generated by G to the power 4. So we have a G is generated by this order 20. So G element of a G is equal to this G to the power 0 is equal to identity, and in the form of this, these are the element of a order of G. Now we have to write H is generated by 4, G to the power 4, then there 0, 4, and then we have are the elements of this thing. Now we have to, by the using this, you can just say that order of these are the 20 elements. If we take a index of this G and H, then you have a, this is equal to, you have a 20, and then order of this is equal to 1, 2, 3, 4, 5, then you have a is equal to 4 distinct right or left cosets are there. So these are the cosets are there 4, 1, H, G square and G square. Each coset consists of a 5 element, because of a we know that the order of H is the same as a cosets. So number of element in the coset is the same as the number of element in the subgroup H. So this is consists of all the elements is equal to 5. Last I will just one more problem I will solve, and then I have to stop. Let G is equal to U30, and then you have to write the element of a U30 which are relatively prime to U30. There are this, and then we have to write is H is equal to 1 and 3, 11, that is clearly the subgroup. Now we have to write is equal to 1H is equal to H. Now we starting the 7H, we have a 7H is equal to 7 and 17, then we have a 13H is equal to this, 19 is equal to 19 and 29. Then again if we take a after 19 you take a 23H, so 23H is given that this is 23H is equal to, you have a 23, and then again remainder is equal to 3, then it is the same as 13H, and then if you take a 29H, then 29H is equal to 29, and then 19, then you have again is a 19H. So there is a total is equal to, you have a 4 distinct coset. If you buy the index set, we can just set the index of this. We can write order of a G is equal to, you have a 8, and then we have a 2, then is equal to 4. So there are 4, and then you know that this is G is abelian, so right and cosets are the left coset are the same. So this complete the portion of this cosets Lagrange's theorem section, and so I think you have understand all these things very clearly. I try to solve some of the problem we have to writing the solve the what is the finding the using the applications of Lagrange's theorems and find the cosets of this problems. So this now I stop today lecture here, and now in the next class we continue for the next topic. We have to start the normal subgroup in the next class. So thank you very much.